Hey friends, Janky here, and welcome back to Odyssey, a scientific adventure game where we're trying to rescue a scientifically minded family who's curious about archaeology and civil engineering and all sorts of interesting things. And they are stuck on this island because of pirates, guys, and we gotta help them. We gotta help them out. So we are doing just that. We are helping out our dear weird family friends by solving their puzzles that they've left behind. Their various puzzles and combination locks and traps and things. And we are going to help them out. So, in the last episode, I believe we just saw where they were hiding across the way from the top of the radio tower. So we're headed back up to the top of the first little island here, back to the observatory tower thing, so we could get across the other side to the big part of the island, so we can hopefully find the family and help them out, get them off the island, as it were, because we're terribly clever people. Oh, and we need to change things up a little, I think, but there's a crank here that I think we need to crank first. Yes, I think that'll get us where we need to go. So, if you recall from a few episodes back, we needed to make a lunar eclipse to open that door. So the way to get the other door open is to create a solar eclipse. And that should open our other door. Sweet. And this plank leads right out. And we can just ride our zip line straight on over to the big island. Sweet. And somewhere over here should be the family. Time to go help them out. I just don't know where to go. Down here somewhere, probably. Hey, more solar panels. Sweet. Yes, let's... Oh, sweet. More journal pages. As you know, if you've been watching, the journals guide us through the various puzzles, through highlighted text. Also a lot of other really cool text, but I mostly skip through that because there's a lot of it, and I'm trying to skip through that part. Anyway, today we explored the main part of Wretched Miner across the last rotating bridge. We mostly found stuff the army left behind, more shacks and watchtowers and things. The first thing Sid wanted to do was get the other zipline working to ride down from the bunker to the main part of Wretched Miner. The ziplines were very sturdy and didn't require much repair, so Mom helped him fix that first. Sweet, ziplines. Okay, so lots of the shacks also had a lot of electrical switch boxes, which we've been opening as we go. So now they're moved on to the main part of Wretched Miner. Ate breakfast. So we talked about, trajectories. Sweet. At breakfast this morning, I asked how Aristotle's physics said the Earth can't be going around the sun. Dad told me two big ways. For the sun to rise and set, Earth must rotate. But if it did, then every rock on Earth would be naturally moving in a circle. That's what ether does, not Earth. Anything made of Earth only ever moved in a straight line toward the center of the universe, which for Aristotle was also the center of the Earth. That meant if Earth is not at the center of the universe now, then all the Earth would be rushing in a straight line toward it wherever it was at a tremendous speed. This would leave behind animals and such, which fall slower to float in space as the Earth zoomed ahead of everything else toward the center. This was because, according to Aristotle, heavier objects, meaning they have more element Earth, fall faster toward the center of the universe than lighter objects with less of the elemental Earth. The natural speed of an object is proportional to its mass, so a boulder that is 10 times heavier than a small river stone falls 10 times faster. Galileo disproved this, but here we go. It looks like I'll have to make actual measurements, which Dad calls quantitative analysis. This game is so sweet. Okay, so we draw horizontal axes. We have distance fall, time fell, that good stuff. Okay. Here we go. You calculate the slope of a line on a graph by dividing the vertical size of an interval by the horizontal size of that same interval. So for example, you would take rise over run, so 30 divided by 3, and you would get a slope of 10. You can calculate slope as the total distance divided by the total time. Or you can calculate it by taking any smaller section and calculating the distance in that section divided by the length of time in that section. For example, we have 1 over 10, which, of course, 10 divided by 1 gives you 10, or 20 divided by 2, which also gives you 10, or 30 divided by 3, which also gives you 10. Very cool. One can also make a speed-time graph where the vertical axis tracks speed instead of distance fallen. For an object falling at a constant speed, the speed-time graph would show a horizontal line. The speed-time graph, for my example, above would look like this. Since the distance is speed multiplied by time, one can get the distance fallen by calculating the area of the rectangle represented by the speed multiplied by the amount of time traveled. So for example, we could say over 1 second, it traveled a distance of 10 meters per second. So we know that it must have traveled 10 meters. Sweet. Get out your calculators. Time to do some math. And then, of course, Aristotle was entirely wrong, because things fall at the same speed in a vacuum. Okay, so we're looking at slope. Okay, so the slope of this. Ah, I see. Okay. So the slope of the red line, I'm trying to figure out what these are here on the side. It appears to be 60 divided by 6. Yes, so that's 10. Which I suppose you could say is the same as 30 and 3. The yellow line is 60 divided by 10, which is 6, which is the same as 12 and 2. Then we have the green line, which is 60 divided by 12, which is 5, which is the same thing as 3 and 15. Then we have 60 divided by 15, which is 4, which is the same thing as 5 divided by, or 20 divided by 5, which means that this must be 60 divided by 20, which is 3. Sweet. Math. Math. That's good stuff. Learn your math. Okay, so let's head on down, follow the wire. This should lead us down to the bunker, I assume. Is there anything else? No? No? Okay. Let's keep following the wire down. Oh, here's another crate. We should probably go ahead and smash that and get whatever inside. Oh my goodness. I get a feeling that this math is going to get harder. That's okay, I guess. Alright, let's see. So we keep following this. And this goes up to this watchtower. Okay. Speed. Okay, so constant speeds. Let's see. 30. So 30 and the time in seconds. So are you asking which of these would be 30? Yeah. So for the first one, that'd be 5 and 150. which I suppose must mean that that one goes at the top there. 25 would be 104, which would be that one, yeah. And then 20 would be 80 and 4. That makes sense. So flip those two. Oh, and I guess the other ones were already in place. Sweet. Sweet. Math. Let's go see what there is to see then. Oh goodness, there are multiple chords. Oh, here's another box. Oh dear, it's more. Okay. Are we gonna start learning about pendulums or something? Okay, here's the next thing. And another sheet of journal entries. Yeah, let's go ahead and do these. So, let's go ahead and follow the cord up to wherever it goes, and then we can read the journal when we get there. I assume all of these are going to come into play later at some point. Let's head on up to the top. Elevator to the top. Okay, so, journal. What do you got to tell me? Right, so we're talking about different things. Okay, the 10K stone would fall faster. The two stones fall each other apart. As soon as the string gets taut, the two stones would fall at the same speed. So maybe the lighter stone would speed up, the heavier stone falling down on it. Fall at some speed. Between the speeds, they'd fall separately. And that doesn't make sense. According to Aristotle, an 11K stone falls faster than a 10K stone. But I figured out that the two stones tied together with a string with a total mass of 11K would fall slower than a 10K mass does, not faster. Well, that can't be right. I asked Dad about it, and he said I had performed a thought experiment, which is a very helpful way to explore natural laws. And when the result doesn't make sense or contradicts each other, it usually means that some element of the thought experiment was wrong. I wondered if maybe Aristotle's idea that naturally falling speed is directionally proportional to the mass is the part that's wrong. Dad said the only way to prove the experiment was actual physical experiments. So now I'm back to wishing it was tomorrow already, so I can drop rocks from the radio tower. Drop rocks. They should have fallen at the same speed, essentially. Okay. I held the feather and the twig horizontally. I dropped them at the same time. The twig fell a lot faster, but I noticed it fell straight down smoothly, whereas the feather swayed and fluttered to the ground. Okay. The feather fell faster vertically than it did horizontally, though still not as fast as the twig. It looked like an object can fall at different speeds depending on its orientation. It looked like the feather was floating on air as well. When it's horizontal, it must hit more air resistance and fall slower, like how a piece of paper dropped horizontally glides down slowly, with so much air hitting it from below. But if I crumpled it, it had less surface area and encounters less air resistance, so it falls faster. Okay. So, blah, 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 blah. I had to watch in slow motion to be sure, and the steel ball did land a moment sooner than the rock, but by less than a second. According to Aristotle, when the steel ball hit, the stone shouldn't have been halfway to the ground yet. Nice. Okay. Dad said to repeat the experiment in water, but he wouldn't say why. So I went to the beach. The surface was churning around too much with all the waves, but I got an idea. I went back to the lagoon by the radio tower, closed the door to the caves, turned the sump pump around, and turned it on. In an hour or so, I should have the lagoon filled up again with nice, still water. Sweet. Okay, so what it's asking here... Oh, okay. So the steel ball would probably fall the fastest. followed by the rock, followed by the twig. Yep. And that all has to do with air resistance. In a vacuum, they would ideally fall at the same rate. True story. Okay, so let's go figure out what the next challenge is. Onward. Okay. Up in here, up in here. Okay, we're getting to another set of pages. So, I think I'll call this one here for now. Ooh. What do you suppose this is? Well, I'm sure we'll figure out here in just a minute. So, I hope you guys enjoyed yet another episode of the Odyssey with me, Janky Shenanigans. If you did, you can totally leave a like down below. Comments, positive or negative, leave those below as well. More than anything, I hope you had a lovely day, evening, or whenever you have to be watching. And thank you so much for watching. Until the next time, this is Janky Shenanigans, signing out. Hey friends, hope you liked the video. If you did, you can find more of my content in the links off to the left here. And if you really like my content, you can become part of the year of 1,000 subs here on the channel and use that button down below to subscribe. But more than that, I hope you have a lovely day, and I hope to see you in the next video.